In our last episode, we mapped the phase space of autonomous systems to locate points of perfect equilibrium. We watched vector arrows converge, locking the system into a single, stable node. But that mathematical perfection is an idealization. Real physical systems do not exist in a vacuum. Take an offshore wind turbine. Structural materials degrade over years of service, while ocean waves and turbulent winds apply relentless, time-varying forces. When time explicitly enters the state equation, or when internal parameters slowly drift from their original values, the system transitions from autonomous to non-autonomous. The math is no longer stationary. Because these physical conditions change, static equilibrium models eventually fail. We have to learn how to track a system's behavior when its underlying mathematical structure ruptures. That structural rupture has a formal name, a bifurcation. It occurs when a smooth shift in a parameter forces a sudden change in behavior. A static resting point might suddenly split apart into a continuous oscillation. So, how do we track these changes, test for stability, and solve the equations when these bifurcations occur? We use a three-step analytical pipeline. Step 1. We map the exact boundaries of these behavioral shifts as the control parameters vary. Step 2. We test the orbital stability of the newly spawned cyclic behaviors. And Step 3. We derive closed-form mathematical equations to define these new orbits. Mastering the relationship between bifurcations, Floquet theory, and analytical approximations provides the technical basis for analyzing systems where stationary models no longer apply. The most basic mechanism for the creation and destruction of fixed points is the saddle node bifurcation. As a control parameter shifts, a stable node and an unstable saddle point slide toward each other. When the parameter crosses a critical threshold, let's call it r equals 0, they collide and mutually annihilate. The equilibrium point simply ceases to exist. To track these collisions over a range of conditions, we build a bifurcation diagram. This chart plots the control parameter on the horizontal axis and the state amplitude on the vertical axis. Reading this diagram requires standard notation rules. Solid lines represent branches of stable equilibria. Dashed lines represent unstable repellers. Here, we see the stable and unstable branches meeting at the exact moment of annihilation. Other zero eigenvalue bifurcations follow similar mapping rules. In a transcritical bifurcation, intersecting points exchange their stability. In a pitchfork bifurcation, a single stable path breaks its symmetry, splitting into multiple distinct states. The bifurcation diagram identifies the parameter values where a specific state loses its stability. It defines the operational thresholds engineers use to prevent structural failure. Sometimes a fixed point doesn't disappear. Instead, through a Hopf bifurcation, it loses stability and spawns a continuous repeating trajectory known as a limit cycle. This introduces a mathematical problem. Because the state is now continuously moving through time, the local Jacobian eigenvalues we relied on for static points can no longer define the system's stability. We solve this using Floquet theory. We begin by linearizing the system, taking a small mathematical disturbance vector and superimposing it directly onto the limit cycle. We then track how this disturbance vector behaves as the equations flow around the limit cycle for exactly one fundamental period. We want to see if the vector grows or shrinks by the time it returns to its starting position. The mathematical result of integrating over this full period is a fundamental matrix solution. We call this the monodromy matrix. To determine if the periodic orbit is stable, we extract the eigenvalues of this monodromy matrix. These specific eigenvalues are known as Floquet multipliers. This is a 2D graph representing the complex plane, which we use to map the Floquet multipliers against a prominent unit circle. The stability rule here is absolute. If all the Floquet multipliers lie strictly inside the boundaries of the unit circle, the periodic orbit is asymptotically stable. Any physical disturbance will decay. But if even a single multiplier crosses outside the unit circle, the orbit loses stability, triggering a new secondary bifurcation. Floquet theory provides the definitive mathematical proof of whether a complex, time-varying orbit will persist, converge, or catastrophically diverge under real-world perturbation. Once we know an orbit is stable, we need to compute its exact shape. Henri Poincare laid the historical foundation for analyzing these nonlinear perturbations. Standard perturbation methods attempt to build solutions using power series of a small parameter. But for oscillators, this creates a mathematical error known as a secular term. Secular terms ruin the mathematics because they force the theoretical amplitude to grow linearly over time. This physically violates the bounded nature of steady-state oscillation. You cannot have a steady limit cycle that expands infinitely. The Linstead-Poincare method solves this. Instead of only expanding the amplitude, it treats the unknown frequency itself as a power series. By carefully tuning the coefficients of this frequency expansion, we can mathematically force the secular terms to zero. The result is a valid, uniform model of the orbit. However, when systems have stronger nonlinearities, simple perturbation methods fail entirely. For these cases, we use the harmonic balance method. In harmonic balance, we assume the solution is a truncated Fourier series. We substitute that series back into the original differential equation and balance the harmonic coefficients until the residual errors equal zero. These analytical approximations determine steady-state solutions without the errors of simpler series expansions, allowing precise system tuning without total reliance on numerical simulation. We now have a complete workflow. First, when a physical parameter shifts, we map the resulting structural breakdown on a bifurcation diagram. Second, when a limit cycle emerges, we prove its orbital stability by ensuring the Floquet multipliers remain inside the unit circle. Third, we analytically define the exact waveform of that stable orbit using harmonic balance. But what happens when we push the control parameters too far and the periodic assumptions break down entirely? When Floquet multipliers sequentially escape the unit circle, they trigger period doubling cascades. The system's orbit becomes endlessly complex, wrapping around itself without ever exactly repeating. In our next episode, we will navigate these cascades, map strange attractors, and enter the regime of deterministic chaos. Mapping and solving periodic orbits identifies the transition points in a system's behavior. It marks the final region of predictable order before a nonlinear system descends into chaos.